Especially this space of program scripting for so this is what program scripting by the this phase was designed for program scripting code. The Windows code. It's code that does not want to use no code. I'm not so it's code oh.
Indeed, I use this library for my professional applications, and I was discussing my dilemma on the Discord server with my friend Jack. I couldn't decide, should I create my own matrix vector library, which is a little bit reinventing the wheel, or should I use a third-party library instead? And he very decisively said, well, if your goal is to learn about wheels, then there's nothing wrong with reinventing the wheel. And I agree, but I didn't want to go as far as doing operator overloading and things like that. The reason being is I know quite a few of you that 10 minutes ago implemented other platforms. So luxuries like operator overloading might not be available. So I've come to a hybrid is attacking the view. Rather than make specific modifications to the vector and matrix classes, I've decided to create a bunch of utility functions at the main class. We did actually do this already with the existing code, but I thought I'd try and make it a little bit more consistent. So for example, add two vectors, I created the vector add function that takes the two vectors results and creates a new vector as the output. And I will fully hold my hands up and say that I've made no attempt to optimize this code before. I want it to be educationally informative, not obscure due to optimization. And so we have a vector add function, you also need a vector subtract function. And how about scaling functions, so we can multiply and divide. We know the dot product is important, so we'll have one of those too. Since we've got the dot product, we may always have normalizing and getting the length of the vector. And we know from the previous video when we've been creating models, the cross product is quite useful to have too. We already have this multiply matrix vector function, but it does some weirdness here to normalize the final result. I want my new library to be quite consistent, so I'm going to replace multiply matrix vector with matrix multiply vector. But you'll notice that this is introducing a fourth term requirement into the vector class. So we'll need to add that too. As with the vector utility functions, there's quite a few matrix utility functions we might need. We can create an identity matrix. And how about the three rotation matrices we've already looked at in the previous video? Translation matrices are also useful. And in the very first video, we looked at constructing projection matrices. So I'll capture that as well. One important function that we have in the matrix library, which we've not done yet, is matrix-matrix multiplications. So I'll include that. And there's one more which we'll develop during this video. So now we've got this modular function that can convert existing code. We no longer need to manually create a projection matrix. We can just solve the functions to it for us. I'm also going to remove the standard cube code now. I think we can do things a little bit more sophisticated with cubes. Now we can load object
Ibyo kongera gukora story byose yanjye none.
Eka. Ni no umuntu yazengera.
Iyo ndi programming ariko cyari hasi. Ikiza.
Na max.
Hano ni ukushyiramo features umuntu ashaka designing umurongo. Ndi none uko yarayigusuye kuri YouTube. Hano umuntu ashaka kuba yashyiraho umurongo, noneho umuntu ashaka guscriptinga adashaka kudesigning. Yapanga mu import line. Ibyo umuntu ashyiramo import line agahita scripting umurongo. Kuko urabona hano ndi ku scripting none ukora kwa mu access ari kugenda hinduka. Kino rero program ariko
iyo mirongo washanyije ukoresheje command.
Uya ni programming. Wangu kuri sortinga hano kuri kugenda imwereza position ya rotation angle fano nganje na program rotation nono nabandi guhindura axis ikabinyereka muri z turuguhindura axis anga muri y undi iyi nayo iri muri generative design ndi kwiga bashaka kugira ngo noneho version ikabiri mu nagiye byatoye kugira design house igiti ishushanya igiti nayirengari inyuma muri code man chakora boro ya n'amabasi yicikaba hana bashyira ku ruhande ariko ntabwo byoroshye gusa ibitambo byinshi ariko igomba guhinduka ndakeka ko nshobora kuyirangiza turinde urugero kamyindure ari abara rya axis iri bara rya axis neka ko rigiye gusa riba cyane abona ko bahise rihinduka yahindutse cyane kandi urabona ko command prompt yayo code prompt kubikora nka zoom ariko in rotation ntabwo ari zoom ya graphics font rotation iri gukora iyi ni shaman kugira ngo iyi board ndi gukora nshaka kugira ngo izajya ikoreshwa n'aba 3D artist 3D designers hari no mukubwira bakoreshwa n'abantu bakora games niyo mpamvu nashizeho kino gice cya Ghost Script Engine muri kamo Ghost Engine also need element pursuit this script engine is designed for
bijyanye na none bya game
amagames abantu bose bakoresha ibyo muri 3D ubu ndacyari ku bantu bakora ibishushanyo ntabwo ndagera kuri rendering phase motion graphics ni abantu bakora ama video editing ariko biriya muri gaming babyita animation ku bantu bakora ama game abantu bakora ama 3D programming 3D engines game engines babyita motion graphics ku bantu bakora ama video editing no fibrate dukuru ubona ubutse bari gukora ama graphics kubera remeye ubundi ndi bishyiramo hano mu mashini ikora engine ikora ibi byose ndi gukora none ikaba ifitemo n'amajwi nka gutya niba ndi waza kubibona kuko hano engine nakozeyo ifite ubushobozi bwo kuba kumva ko iyo inyuma yifitemo na moyo cyari gato cyari kuri zone ako urumva ko inyuma kintu kijyanye na universe system ubona yanjye system no kujya mu muhanda ukumva imbere ziri kuvuka imodoka man game engine ni ikintu utwo game engine ni twari myaka 10 ariko umugame engineer ahembwa amafaranga menshi kurusha umwatsi kurusha umushushanya akubye kabiri igiciro cyayo kuko ibi bintu ntabwo wabyiyamura mutazi imibare na physics waba ugiye gusa niba umuntu ukoresha engine yawe agomba kuba azi imibare kugira ngo abe 3D designer mwiza ibaze none wakoze engine uri gukoresha imibare wazi kundi biga ariko nyine ibintu byose bisaba kwitandatu man uzi iyi stream ndi gukora kuri YouTube nayo buri urimo man nawe uzi ko buri urimo tuzabona kamera itari kwaka ibi somo ndi gutanga flash kaje kuyikoresha tu ibyo soft ndi gukora ndi kubona ari gusambanye nda sometimes I don't do coding I need to know coding so ariko kumva indi ira advanced cyane ndi kwirekoding ndashaka kugira ngo aya ma controls none ngenda gira gutya control zigende imanuke cyo turabona cyangwa tubiri gukora ama function tize naje kuyakora ntabwo biba byoroshye naje kuyaprograminga ku muba wacu n'urasene mukanya ni kuko ndava mu saa 3 nshobora kuza kuguhamagara to uyu mujine wa muntu wa mbere namenye C++ mu buryo buri advanced tu no umuntu w'umwongereza akora nawe C++ 3D programming n'umusazi mu mibare we yakwirukansa ugatana ndagasa umujine umusazi bya danje amwita Javidis umujine umusazi bya nyuma
So this is the effect that we're looking for. Assume I've got an object. Object will have an origin point, and the vector represents the forward axis of the object. Let's say I want this arrow to point at something in the scene. One option is, of course, I can specify the angle theta between the forward direction and the direction of the point is.
Especially I'm sorry my screen was not starting correctly. But really tough for me to destroy.
Location, i.e., I want to come up with a transformation which converts this forward direction to
Back
this
on
forward direction. So I can just express the lookout direction as a vector. And we can extend this idea further. Instead of assuming that we're doing everything at the origin, if I assume that this is our I point, I can place the object anywhere in the 2D plane, and so it's another location. And conceptually, I feel that it's much simpler to think about than working out the angle of a moving object. So here I've got an axis in 2D, and let's make this assumption that everything we can do in 2 dimensions, we can do in 3 dimensions, by simply adding an additional term. Here I've got y and x, and I'm going to place point P at location 1, 1. With a rotation matrix, I would create a matrix between the space outlined in black and the space outlined in red. This would be my angle theta. Assume my point P would also rotate to a new point, which I'm going to call Q. What I want to work out is where does Q exist in the original space outlined in black. But instead of specifying theta, I'm going to designate one of my axes to be the forward direction. In this case, it's going to be x. I'm going to represent that direction as a unit vector. Once we have the forward vector, we know that then that is perpendicular to that forward vector must also represent that the equivalent y-axis. So we can generate the unit vector to represent the other dimension. So in this rotated space, our point Q still exists at 1, 1. But clearly in the original space, the location of Q has changed. Once we have the unit vectors from this space, we can break it.
Especially I'm sorry for skipping this track.
On the bottom here, this distance, we're going to call AX. This distance, AY. And we can do the same for the other axis. This one, BX. This one, BY. If we look at where Q exists in the new space, and where P exists in the new space, and we have to carry this on beyond the axis, we can say that this distance here is in fact P x forward times AX, and P was left at 1, 1, so it's just simply AX, and this distance here is P multiplied by BX. So what we're referencing is QX equals AX plus BX. When P is a location 1, 1, and it follows that QY equals AY plus BY. Again, when P is 1, 1, we can extrapolate that if P was 2, 1, we need 2 lots of AX. If P is 1, 1, we can scale these values accordingly. So we end up with QX equals BX AX plus PY BX. And PY becomes PX AY plus PY BY. And so, by declaring a vector as being the forward dimension, calculating a vector which is normal to that in the same plane to give us an opposing axis, decomposing those vectors into components in the space of the original axis and scaling those components accordingly, we can come up with a matrix that is effectively a rotation, and all we need to supply is the direction that we're declaring as forward. But we have a second equation of this, we probably want to try and represent it as a matrix. So we can think about it like this.
kandi nibyo gutekereza kumwe na ribisi
And if you remember from the previous videos, on multiplying this matrix is dx times ax plus dy times bx becomes qx, and likewise with q1. So in 2D space, we've come up with a simple way of rotating space based on the direction vector. But this is so far assumed that we're doing things rotating around the origin. What if we want to rotate around a point in space? Well, as with 3D, if we want to do translation, we need to add another component of vector and matrix. Let's assume the point we wish to transform is dx, dy, and 1. We're going to need a 3 by 3 matrix now to do the transformation. What we know already that it's not a matrix is what we've already got. Ax, ay, dx, dy. If we want to do a translation, all we want to do is offset the coordinates. This will be values multiplied by 1. So we'll say dx and ty are located in 2D space. Our third column will fill it as 0, 0, 1. So now, all we need to do is specify a forward vector, derive an orthogonal vector, and provide the translation. And we've derived in 2D a matrix which will transform any set of points according to these criteria. And it goes without saying that the 3D is a very similar format, and we can have the exact components of the point. But we also need an additional vector in our 2D space. So here we can start to see a pattern. We've got A vector, which is our forward vector. We've got B vector, which is orthogonal to our A vector. And we've got the C vector, which is orthogonal to both. Finally, we can offset our origin point by point T. And I'm going to call this the point and matrix. It's one of the names we do a lot of forward, right, and forward. Although the order of these may change under application, we can use our point and matrix to position and rotate an object in our world space, like any of the other matrix transforms we've been doing. And this in itself is very useful to make the scene look lively and interactive. Objects that follow look at other objects in the game. And so far in the videos, we've always assumed that the player or the camera is at location 0, 0, and it's looking there on the axis. 3D is there, and the 2D level is looking along the x-axis. But since we now have a transformation where we use the direction and a point, it would be ideal to use this as a camera. The point-back transformation has worked out how to transform from the origin point to this location, but the camera needs to do the exact opposite. It needs to take all points anywhere in space and transform them back to our original 0, 0 looking along the single axis. We want effectively the inverse of whatever this transformation was. And before I go any further, I am not going to talk about how to invert the matrix. It is well beyond the scope of these videos. Fortunately for us, and this only applies to major sheets that can rotate and translate in the scale of this sort of work, there is an established routine for inverting this matrix. And I've drawn it down here, and I'm just going to treat it completely as a mystery black box. So please note, this is the correct procedure for all 4x4 matrix sheets. This only works in this instance. And visually it's quite nice because we can see that our A, B, C, and D vectors still exist in the inverted form. They've just been transposed. But our translation vectors, they now become the dot product between our translation point and one of our axis vectors, subtracted from 0. And so whereas before this was our point at matrix, I'm going to call this one our look at matrix. And so once we've transformed any object's coordinates into the world space, we can multiply by this matrix to translate it into view space, i.e. looking through the lens of the camera. And we can position that camera anywhere in the world space, and we can make it look at almost anything in world space. And so now I think it's time we add a simple first-person shooter loading camera to our engine, so we'll be able to walk forward and backwards and rotate on the spot. We'll also add a little depth so we can get to know elevation to seconds. I always find it useful when working with cameras to have a 3D object that represents the axis and the directions of those axes in space. Because when we start playing with hands, things get weird quickly. After we get bored. I'm also going to confuse myself around the world of spin around levels. So I'm going to remove the detail thing. I'll still apply the rotation, so there'll just be no rotation. Good. So let's take a look. Well, we can see something perhaps of this axis. Certainly, it looks like a graphs collector on a quantum. We're going to add an additional function to our matrix utility function set called matrix point path, which, as we've just seen, requires a position vector where the object should be. The target vector is kind of the forward vector for that object. And a forward vector. Creating the forward vector is easy. Simply subtract the position vector from the target vector and normal. Even though we provided a look vector at the start of the input for this function, the actual look vector might change because our new forward vector may have a wide number of pieces in elevation. Effectively, this is the equivalent of pitch, i.e., the speed rotates along the x-axis. We can create a new look vector by looking at how much of our described look vector projects onto the new forward vector. And we can adjust the described look vector accordingly. Creating the new right direction is quite easy. It's just the cross product of those two new vectors we just created. And then when we manually construct the point out matrix, we just need the slides. If we invert the point out matrix, we can create the lookout matrix. And this version only works for this specific type of matrix. So I've created a function here called quick invert, which simply does that inverting for us. This means we can now add a camera matrix into our transformation chain. We'll have a look vector which is defined as 0, 1, 0, so that's pointing up the y-axis. We already have a camera vector, but I'm going to add an additional vector called look direction. And ideally, this will be a unit vector that travels along the direction we want the camera to point. So along with that look vector, I'm also going to create a target vector. I'm going to set the target vector to the current camera vector.
urabibonye oya mani tugiye nkora amarayivu kuri kodinda uko no live tugiye mbona internet iri kumbana ibibazo iri kugenda ku mashini yawe mani numva kuri kodinga imashini nabonye iri kuremererwa Tamukata yuko igenda ikura amalive n'amalive nayo yuko ndi kuyabona internet iri kunzanira ibisazi bito.
So I'm going to have a triangle view of this. And so before we project the triangle, we no longer want to go directly from the world space straight to projection space. We want to go through our view matrix. So we'll multiply our triangle.
Man, we live.
This one view, the view is triangle.
Biba byoroshye mani
So here I'm going to open down these, which will increase or decrease the camera's light position. Right, so I press down. We can see the object is moving. In fact, we can see beneath the object. We can see this actually an axis, so that's pointing along the Z axis. Up here, we have left and Y. Also adding left and right, so we can see what happens along the x-axis. Oh, I can move from side to side. Very nicely, we can start to see the axis pointing which direction is which. And this is quite nice, because what we're doing is moving the camera around the scene. We can choose to think about where to place the camera and how to move it around. If we want to create a first-person shooting style camera, a very simple one for this. We need to think about what direction is the player facing. And this is effectively a rotation in the y-axis on your camera. It's traditional using the WASD keys in the first-person shooter. So if we use recipe A key, I want camera forward backwards is a little bit more involved because I want the camera to travel along the look vector that we created before. So I'm going to create a temporary vector called P4, which is a scaled version of the look direction, and it's still quite speedy on the mover, because we can assume the look direction in this case will be normal. And because we've integrated time instance, we've effectively created a forward velocity vector. So in order to move our character from a building key we want to add to our camera's location this velocity vector. And likewise, we want to do the exact opposite for moving back. So we subtract the velocity vector from the current camera location. So what do we do with this yaw value? Well, our point time matrix requires a forward vector, which we currently set as the target. However, our forward vector is actually going to be rotated by the yaw value. So if I specify this to be a fixed vector, just heading along the z-axis, and I create a rotation matrix to rotate around the y-axis yaw radius, I can rotate my target vector by the rotation matrix to produce a new look direction vector. So I can remove this line. So this vector is some unit vector rotated around the origin, but now we need to offset that to the current camera's location. So we take the target vector fixed along the z-axis, we rotate it by yaw radius, which simulates turning the flare from left to right. From this, we get a new forward facing vector, which we add to our camera location to give us a target for the camera to look at. So let's take a look. We've got the scene, and I'm going to move the camera forward a little bit first. Now I'm going to walk backwards to zoom out a bit. What we can see, the axis is very clear. To the left and right. I can steer. Backwards, forwards, I'll smooth down a little bit. There we go. Let's go. Oh dear. Deary, deary me. Oh no. What's gone horribly, horribly wrong? Well, we've constructed the same problem we saw in video 1 when the object got 2 levels of the camera. When we're projecting the triangle, it has a Z component which we divide by. And as that Z component gets smaller and smaller and smaller, of course, whatever we're using, our body gets larger and larger and larger. Our triangle gets huge because it approaches 0. This causes a problem for us because our triangle is so big and we're trying to draw. We're getting all sorts of memory reduction errors, we're getting performance problems because we're literally building this not drilling in this case to try and draw. The second problem is that sometimes the triangle is behind the camera. And I just can't comprehend what that means. This means we need to get control of our triangle again. We're going to use the process of chopping a triangle into small shapes. Before we start talking about physics, I think it's worth thinking about the differences between programs and mathematicians. Consider in 2D space, we have a line. Now, as you see, one of the things that we're taught to represent line is y equals mx plus c. And this is nice for programs because we can sequentially go through x, create y values, and plot the line. Mathematicians don't think like this. Instead, what they see is a concept where there is a state where all of this is true. And so, in the infinite soup of x and y coordinates, there exists only one set of solutions that can satisfy the truth of this equation. And it just so happens that all of those solutions lie along the line. If we consider that m is really dy by dx, which is effectively a vector following the radius of the line, we could rewrite this equation as the y equals dy by dx x plus c. Therefore, it follows that y dx equals dy x plus c. Finally, minus dy x plus y dx equals c. Let's suppose for a moment that instead of having a gradient, what we actually have is a norm to the line. Well, inserting a gradient to a norm is fairly well established. Dy by dx, if you want to invert that, becomes minus dx over dy, which we can say is the same as This is quite useful because here we go to dy. We'll say, let's say, as minus some normal x value. So let's replace that in our formula. And whilst we're at it, we'll take out the x value, which is the same as our normal y value, and replace that in our formula. So this means we can represent our line as x, normal x, plus y, normal y, equals c. Now, c is traditionally the point of the y-intercept. But remember, this equation actually represents the set of all solutions that lie along this line. So we can take any x and y value, which we know lies along this line, and therefore it must be true. So let's take a point that lies somewhere on our line, point P. So we know the location of valid solution exists somewhere along the line defined by x and x plus y and y equals px and x plus py and y. And this is quite a nice form of having because it simply becomes x and x plus y and y minus p dot product and equals 0. So whatever this condition is true, in 2D space, our line will go through. And this means just by knowing a single point on our line and the normal to our line, we can represent the line. And intuitively, this makes sense. So let's say I've got a normal slightly different goes up here, then my line goes like this. So the normal distribution, and my line do something like that. And as we saw before, the interesting is three dimensions. Just but it's not a line anymore, it's a plane. Even if you are on a sheet or surface where all the solutions are practically free, this is the equation. X plus py plus c then equals 0. And it's not to work with this format, it's just the original ones are playing. Spaces. But also, it works with things with quality. And that's all we need to represent geometry. Let's get back to graphic. Start thinking about clear. Now, I'm going to show this in previous using first I want to go on triangle. Everything is out of the line. I want to keep. Come on, give us these original points of triangle. Now, the edge of the triangle and the line is flipping it. Quadrant. Or something. Let's go to this. we say, oh, oh, however, again, we want to yes, yes, the screen needs to be fine. Like this. One big original again, it's quite fun. We think of how but also remember that we're forming zero against this one plane. So ignore the other. So we'll create a clicking function. The mechanism satisfies it, and we'll add those triangles into a queue to be processed further. We know so we will know that the triangle security so that all the remaining triangles as a consequence need to test the remaining edges will test it. And so I'm going to show a video of how to do this algorithm. Triangle, and then for each plane, we set the plane where we split against. I'm going to test the triangle here. Well, then remove here. The triangle will go. I'll then test this triangle using the clipping against the plane. And this will yield 0, 1, 2. I've got all the triangles in Q. I'll have a look at this.
ntabwo ndabikoresha kuko bisaba kuba ufite bijya twitinda kuri iyo opening online kugira cyane kubikoresha offline nabonye iyo nta crack igihe nawe nta track igira ariko izo ni na meya ziriya product zose za autocad ziva muri rwa ruganda ushobora kugira ngo nawe uziyandikishe buto nazo uzikoresha oya ntabwo bigoye no just no
Ese ntabwo ari kwishyura.
oya mayira arenze mayira arenze uyu muntu akivugisha Brenda akabona maya akabona ko neza ageze hano muri hafi mbona amacingo ngo Brenda kuko bafite muri abantu ufite ibihembo kuko hakomeye njya muravuga ati hari igihugu nk'umusazi utaza hano abasazi ya boro wayimenye ngo ndabona ko muri iyi sifidi nta kintu cyagera iragoye kugura iragora kuko icyambere si ubumenyi nta boro ntabwo mu kuyiga niba ikigoye ni ukumenya ikintu ugiye gukora naho software yo nta kigoye niba uburyo gukora ikintu uzi ikintu ushaka no gukora birakorohera nta software n'imwe yakunanira ariko wamaze ikintu uvuga ati iyi software ngiye kuyiga kuko nshaka kuyikoramo ibintu byiza uba uri kunywa amazi uri kunywa amazi uri kunywa ariko wabonye ko mayirenze tu ibyo njye nabaga mbwiraga abantu umuntu mushyashya muri firidi akamenya Brenda aba yumva ko Brenda ariyo tuzi ibaho ku isi irenze ariko iyo umaze kubona imana amaboro menshi ayirenze menshi cyane ahubwo ikibazo ni uko umuntu aba atari yaba porofeshono mu bintu Brenda ni abantu bose nyine bashyashya mu bintu nka biriya bahita babona kuko ari bwo buntu aho usanga nka ziriya zihenze zinagurishwa ariko mu bintu bya firidi maya irayoboye maya na firidi ntacyo boro zirarenze byazamuje ati nawe ati numvaga Brenda irenze Imana wamuciwe hari boro hano hanze zirenze umuntu yibaza na hano zavuye gusa kurenga
ntabwo iri byataje ku buryo imashini zitageze
maya maya ikeneye imashini mani idafite imashini nta kintu wakora gusa za Brenda zidafite imashini yo
oya ndavuga
izuye
za aiga
ya wakora utuntu turi basic two gutuma uyimenya no kutanyura mu ma advanced design na ama advanced rendering ariko gusa izi za hano zatuma uyimenya ukanayimastaringa Someone 13 million. decide for scripting engine third. sorry for taking this streaming camera. I'm sorry. Especially let's close my session here. Tomorrow I will share in the another session for this. Tomorrow I will share in the another session of code. Tomorrow I will share in the another sessions of code. So tomorrow is share on with the screen of code. Share on the screen of code and see the screen if you want the zooming. Yeah. Tomorrow, wait, guys, man, subscribe now. Subscribe tomorrow, share another streaming code. This is the samples of streamings of code. This is the sample. Tomorrow I will share you another thing for hydroxy code. Equal train, graphics, 3D graphics, visually, amount of peanuts to advanced code. Yeah, the CPC graphics was handled by AGR and SFMary codes. Yeah, I'm not getting the entire tubes. So these tests for game scripting, I'm sorry. So this is working for game scripting code. Oh, yeah, it's for zoning. This is for the zoning that especially I'm sorry, the zoning code. This for zooming code. Tomorrow I will share you another screen code. I'm sorry. See my bar codes, especially tomorrow I share you my bar graphics code. Bye bye. It's in my stream here. It's in my stream here. There is a stream. It's in the stream here. Bye bye.